Okay, I think we are a good number. I think we can start. So thanks for joining us today. We are going to talk to you about a solution to improve gas cooler efficiency. So the CAREL chillBooster system. I'm here with my colleague Giovanni Bonesso, and let's see what we are going to present you today. So first of all, this solution for gas coolers comes into the segment of compressor racks. That it's just one of the many segments that CAREL offer in its portfolio, together with cabinets, controller for food service, IoT services, and so on. And as we'll see, it's a solution that crosses many applications. And that's why my colleague joined me today to present it. So let's start with a few words about ourselves. I'm Federico Ferrari. I'm a member of the food retail marketing unit. And I work mostly with compressor racks, condensing unit, ejectors, solution for food retail refrigeration. And I'm here with my colleague Giovanni Bonesso.
Federico, thank you for the presentation. Welcome everybody. I'm Giovanni Bonesso. I'm working in CAREL as a product specialist in the humidification platform. And I'm dealing with adiabatic solution and evaporative cooling solution as well.
So food retail and adiabatic system, food retail refrigeration and adiabatic system. Let's see an overview of what we are going to present right now. So we'll start with a few examples of HVAC and refrigeration applications where you can use gas cooler and CO2. Then we'll see what's the problem here that we are trying to analyze and discuss. So the increasing temperature that we are facing year by year, and that's of course impacting the gas coolers. Then Giovanni will introduce you to our solution, so CAREL chillBooster for adiabatic cooling. And in the end, we are going to check some experimental data to see the performance of our system. So first of all, as I mentioned, why both humidification and food retail refrigeration, and also HVAC. So what we are analyzing here is the CO2 as a refrigerant. So it's a cross solution that's used both for refrigeration and HVAC. So for HVAC, we usually have in both commercial applications and also industry and process ones. We have a chiller most often, that it's responsible to keep a set point in temperature to cool down some water, while the heat is rejected to the ambient. So we have the above mentioned gas cooler that of course is impacted by the air temperature that's working in the ambient that it's working in. We have something similar for what concerns today's presentation in refrigeration systems. Because this time the useful effects, let's say, it's in the evaporators, that it's inside the cabinets where the food is kept. So evaporators in cabinets, cold rooms, refrigerators. Here the CO2 evaporates to get the cooling effect. Then everything is processed by the compressor rack that's responsible to keep pressure set point and make the refrigerant flow. And the part that interests us the most in this presentation, the gas cooler, where the heat gets rejected in the ambient. Again, of course, there is a huge impact of ambient temperature in the gas cooler. Of course, in the same way that there is in the HVAC applications. So let's talk a little bit about the ambient temperature influence in the gas coolers. In the last years, we saw something quite evident to all of us. There has been an increase in the temperature, especially during summer peaks. Considering that many plants and systems has been designed and installed some years ago, even 10 or 20 years ago, it's obvious that the conditions were different. So we are facing, in some cases, that the heat exchanger are dimensioned for other conditions. And sometimes it can happen that right now, during summer, most often, they are not enough anymore to produce the heat rejection that is needed. So what's the effects? There is a decreased capacity in the heat exchangers. They are not anymore enough to deliver the capacity that they were designed for. Also, there are some summer peaks where the hot is too much, and again, it's a matter of not delivering the cold to cold rooms or cabinets and so on. And especially in food retail, this is quite problematic because we can say that it's mission critical to keep the goods at the correct temperature. Otherwise, there will be a loss of goods. Everything that I've just said is especially true for CO2, where since we are working in two different modes, the transcritical and subcritical modes accordingly to the ambient temperature. So let's explain it better. Since the CO2 critical point is quite low, it's around 32 degrees Celsius, it happens that working above this temperature, that can happen with the ambient temperature that we face, especially during summer, we have to work in transcritical condition. That means the CO2 does not anymore condensate in the heat exchanger, but there is just a gas that cools down. And that's why we call it a gas cooler for CO2 transcritical systems. But that means also that to have liquid CO2 to flow in the cabinets and so evaporate and produce the cooling effect, we have to use a valve. It is the high pressure valve to bring it back inside the bell and have liquid to operate with. Of course, it's more efficient to avoid this passage and work in subcritical conditions. So to end this discussion, it's more efficient to work at a lower ambient temperature, as it's obvious to say. So Giovanni, would you like to tell us something about the possible solution that we can have for gas coolers to solve this problem?
Sure. Thank you, Federico. You gave us a really clear picture of what is the problem and the influence of high temperature. So basically, the topic are two: reliability of the system and energy efficiency. In order to mitigate this bad effect of high temperature peak, the solution is not just one. We can have different solutions. So maybe I can briefly show you some of them. One possible solution could be to oversize the heat exchanger. In this way, we can be able to exchange more heat in critical condition. Anyway, this solution is not really a cost-effective one, so it's not something we would suggest. Another solution could be to adopt a wet media evaporative cooler, but again, it is not something that I really recommend, since wet media is installed in front of the heat exchanger, and it will cause pressure drop to the air that is incoming inside the heat exchanger. So the energy consumption is not really optimized in this way again. So we can now jump in what is CAREL solution to mitigate heat peaks and to restore cooling capacity and reliability of the system. CAREL proposal is chillBooster. chillBooster is a system composed by a pumping station and a distribution system that has to be installed on the heat exchanger, gas cooler, chiller, whatever it is. The distribution system sprays water through nozzles, and water is evaporated by extracting heat from the air. Thus, the temperature of the air decreases, and it is able to extract more heat from the heat exchanger. So the cooling capacity is restored from to the design condition. The way to use chillBooster is quite simple. Whenever the chiller or the condenser or gas cooler has a drop in efficiency, the system can be activated in order to spray and cool down the air and restore the design condition. The warmer and the drier is the air, and the more effective is the solution, since the drop in temperature could be higher. Let's see now how the system is composed. I mentioned that we have a pumping station and we also have a distribution system. The pumping station, thanks to its property, its feature, is something that can be flexibly installed, since the IP rate can guarantee to be installed also outside. So we don't need necessary technical room where to install the pumping station. And this allow to be flexible in terms of installation, since usually condenser and gas cooler could be placed on the roof of the building. So we are able to install the pumping station close to them, avoiding any extra cost related to complex installation. The pumping station is divided into main parts. We have an electrical panel on the top left of the picture and an hydraulic part. Since the task, the aim of the pumping station is to take water from the grid and increase the pressure in order to nebulize water through nozzles, the main component, of course, is a pump. The pump is available, have a quite big, wide range. So we have 3 sizes available, starting from 100 liters per hour, 500 liters per hour, and 1000 liters per hour. These allow the solution, chillBooster, to be flexible in terms of water output. So we can fit what is the request by varying the size of the pumping station. One important point that I would like to underline is the hygiene. As you can see in the picture, on the bottom, there is a drain valve installed. The drain valve is a solenoid valve that can be opened through the electrical panel whenever the system is not asked to spray water anymore. So in this way, we can drain out water from the circuit, and we are sure that no water stagnation can be present in the system. To further increase the hygiene, a UV lamp can be installed as well as an optional one. So for those applications that doesn't require necessarily a UV lamp, there is a standard solution without it. But for those installations that would like to further increase the hygiene, the UV lamp can be already installed by factory. Thanks to the radiation of the lamp, bacteria will not proliferate, and so there will be no contamination in the sprayed water. Let's pass now to the distribution system. Distribution system is composed by manifold with nozzles, cap, and valves. Manifolds are stainless steel made and are available in different sizes in order to be flexibly mounted according to the dimension and the geometry of the gas cooler. Nozzles are available, and we have 3 different sizes of nozzles in order to combine the manifold size, manifold length, the number of holes where to install nozzles, and the nozzle size, and fit perfectly geometry constraints of the coil and what is actually the request in terms of liters per hour of sprayed water. at the end of the distribution line, I always suggest to install and recommend to install a drain valve. This valve can be driven by the electrical panel of the pumping station. And again, like the pumping station drain valve, this valve will open when the nebulization is not required. So in this way, we can empty also the distribution system and not only the pumping station. So if the installer perform a good installation, guarantee the appropriate slope to the manifold in order to use gravity to drain the system, we can assure an automatic drain of the system, avoiding any kind of stagnation. Regarding water quality, chillBooster, again, is a flexible solution since it could work with both tap water and the mineralized water. Tap water is something that is usually cheap and available, but at the same time, tap water is not treated water. So according to the water quality of your area, you have a certain content of minerals and particles inside water. This means that when we spray water and water evaporate, the solid contents will not evaporate as well. So they will deposit time by time on the coil surface and on the nozzle surface. And during time, they could somehow clog the nozzle that need a certain maintenance. The maintenance is not really something difficult. It's necessary to clean nozzles with anesthetic solution or just replace them before starting the hot season again. Demineralized water is another option. It is treated water, and demineralized water property is to have a really low mineral contents. So when we spray this kind of water, we not spray minerals, and we avoid any kind of mineral deposits and lime scale issue. Anyway, with this kind of water, the installer and the designer need to consider that it can be an aggressive water against aluminum, for example. So it has to be considered for the installation if the heat exchanger materials are compatible with the mineralized water. Anyhow, the CAREL proposal, in order to minimize the impact of maintenance and the cost of maintenance, is to use demineralized water in order to avoid any kind of mineral deposits. For this reason, in CAREL portfolio, there is also the water treatment system, a reverse osmosis plant that is able to filter the water and remove all the contents, the solid contents. Together with the water treatment system, the expansion vessel can be installed and provided in order to keep the pressure stable before chillBooster and let him work with the proper condition. Okay, we have seen some details of the product. We can now see some installation example. So how the system can be installed on heat exchanger. So here in the picture, we have two examples of really common heat exchanger geometry, the vertical one on the top and the V shape on the bottom. The installation layout suggested is all around the surfaces in order to cover the frontal area of the heat exchanger. And we suggest to place the nozzle spraying out towards the inlet airflow and place the manifold 30 centimeters far from the heat exchanger. In this way, we can obtain the best distribution in terms of water nebulization.
So Giovanni, excuse me if I interrupt you, but I guess so that it's a versatile product that can be adapted to different layout. Is that what you mean, correct?
Exactly, exactly. Is perfectly what I mean. In fact, not only vertical and V-shaped coil are something suited for this installation. Also, horizontal coil can be something suited. We can have in this case two kind of possible layout. The first one is the so-called perimeter one. Manifold and nozzle are installed all around the heat exchanger, and this solution is suggested when the dimension and the water load is not really not big. If we have something bigger, we can think to move to surface distribution below the area of the heat exchanger. One last possible configuration is the W-shaped coil. We have a different V coil with the heat exchanger, and again, we can have two possible layouts. The serpentine one on the top, so we can pass the manifold through the V coil, or a more standard one, again, installing the manifold on the external surfaces. Okay, we have seen how the product is composed, the system is composed, and some example of installation. Maybe you can now show us some controller strategy.
Sure, because as we'll see, chillBooster is perfectly integrated with other CARELs portfolio solutions. So let's focus with PRAC, that it's our best solution for transcritical CO2. That controller is able to manage the compressor rack as well as the gas cooler. And in this case, it has some specific functions thought and designed to control the chillBooster. And what I mean by that, it can be integrated as a safety function to avoid a high pressure alarm. And it's turned on and off directly by the logic of the PRAC. The PRAC by itself then is characterized by an ease of use reached by the evolution of the product that's been around a while, and it's a very consolidated product. And here in this layout example, you see how the chillBooster is integrated in the gas cooler together, for example, with some heat recovery if present. So talking about the logic, there are two main options that can be pursued with the chillBooster. Both are in the direction of energy efficiency and efficacy. But for example, in the option on the left, you see that the chillBooster is responsible to avoid the summer heat peaks. So for a very small amount of hours during the year, some heat peaks happen, and they are kind of an extreme condition considering the normal profile and the standard profile of the temperature distribution. And in this case, it will be quite a waste to dimension the gas cooler for such a rare condition. chillBooster comes to help in these cases to just cut this unusual temperature and let the end user to dimension to size the gas cooler for a more standard condition. On the other hand, another logic that can be pursued is to achieve a better efficiency. You see in the histogram that the consumption are different using the chillBooster or not. And in this case, it's especially true with CO2, because with chillBooster we can operate at a lower ambient temperature, working on a higher quantity of hours in subcritical condition. So let's see a little bit more about the efficiency that we can reach with the chillBooster. We made a lot of study, of course, and the data you see in this slide are the data from a master research from University of Padua, did in our labs, where the data from a gas cooler has been compared using a chillBooster or not. And as you see, the efficiency increase a lot with the increase also of the ambient temperature. Also, in the literature, there are a lot of study about this and the efficiency that you can expect from a system like that, it's around 8 to 12%. This is our presentation. If you have any question, please let us know. Otherwise, you can find CAREL people in our stand, of course. We invite you to visit our booth. And we are available also at our mail addresses. And please contact us for more information. Since our time is almost finished, we get only this question. Giovanni, can you tell very briefly something about the climate where chillBooster is best fitted?
Okay, sure. The drier and the warmer is the outside temperature. For example, if we are in Saudi Arabia, it's perfect. The more effective is the evaporative cooling effect. It means that we have a really drop in the air temperature by performing nebulization with chillBooster. Anyway, also with moist climate, with humid climate, chillBooster will be something effective since it will wet the coil surfaces. But preferably, it is better to use it in dry and hot climate.
Okay. Just a note from my side. From our experience, we saw that maybe when it's impossible to avoid the hot peaks, so high pressure, because maybe it's humid close to a sea area. Maybe another option is to use ejectors to take advantage of this high pressure and recover some work, talking, of course, about transcritical CO2 system. I think with this one, excuse me, there is a question. An attendee asked if chillBooster can be used also on Freon systems. Yeah, chillBooster can be used in each kind of system with each refrigerant. We focus this presentation on natural refrigerant because of the benefit we highlighted with CO2. But of course, decreasing the ambient temperature is always a matter of increasing the efficiency. So the answer is yes, and also because it's a versatile solution, it can be applied in each kind of heat exchanger and condenser, as Giovanni showed many examples. So
exactly, for both new installation and retrofit if necessary. So doesn't matter really the refrigerant.
I think with this one we finished our time. So I thank you all for coming.
Thank you for joining us.
Let's keep in touch and come visit our booth in the VTS. Thank you.
Bye.